is all about nuclear energy. We first need to talk about radioactive decay. The radioactive decay occurs when the nucleus of an atom breaks down to produce one or more different elements from the original. Unstable nuclides may be referred to as radioactive isotopes or just simply radioisotopes. The heavier an isotope is, the more likely it is to be unstable. This is why if you look at the periodic table, especially the one in the classroom, those are the ones that are outlined. Those are your man-made elements. Literally, their lifespan are less than a nanosecond, some of them. And they can only be found in the lab because it's in a controlled environment. And they know, based on the nuclear reaction, that it's going to be produced. That's why those have been the last to be discovered, because of that lifespan that they have. So again, the heavier it is, the more likely it is supposed to be unstable. Just think about humans in general. Humans are the same way. Typically, the heavier you are, the obese and things like that, typically you relate to being unstable, health-wise. There are 3 types of radiation: alpha, beta, and gamma. Alphabetically, A, B, G. Okay? You have to be able to know their types, and you have to be able to tell me their Greek symbol, isotope symbol, what they resemble, their charge, and their mass. So let's start with the alpha particle. Alpha particle, the Greek symbol for alpha, simply looks like a or sort of like a fish. The isotope symbol is 4,2He. So if you see this in a nuclear reaction, if you see 4,2He in a nuclear reaction, this means that alpha particles were involved somehow. Now it has this isotope symbol because it resembles a helium nucleus. Again, just the nucleus, not the electrons are present. Now, since it's just the nucleus of a helium, since it has that 2 there, meaning 2 protons, this causes it to have a charge of 2+. Also, with the 4 there, that means it has a mass of 4. Beta resembles an electron, so its symbol is 0, -1e. It has that 1 electron that it resembles, therefore it has a charge of -1, and since it also resembles an electron, it has the same mass as an electron. Gamma rays, they don't have an isotope symbol because they're not represented in a nuclear reaction. They're high energy photons, so they're energy, so they have no charge and no mass. This picture shows their strengths. So you have paper, wood, and concrete. Alpha, being the biggest, is the least penetrating ability, so it cannot even go through paper. Beta can go through the paper, but it cannot go through the wood. Gamma, being the strongest, goes through the paper, the wood, and even some can get through the concrete as well. So think about the Hulk. Hulk can break through anything. Gamma is the same exact way. Okay, in a nuclear equation, you're going to have to be able to tell me the radioactive decay that's being produced or captured based on what you see. So first, we need to be able to tell me what's being produced or captured, whether it's alpha particle, beta, or, well, gamma's not represented. So let's just go through that first. So in this first equation, what do you see? You see a U, a TH, and a HE. This right here is the symbol for alpha particle. So this means alpha particles are a part of this nuclear equation. The second one, what type of radioactive decay do you see? You have an electron sitting here. This means you have some sort of beta. Same thing happening with the third one, beta. Now, based on the location of that isotope symbol, you should be able to tell me whether it's being captured or emitted. Capture meaning it's being taken in, emitted means it's being produced. So if the isotope symbol is on the left, it's being taken in to the system. If it's on the right, it's being produced. It's being given off. So it is emitted. So in this first example, alpha particle is to what of the arrow? It is to the right of the arrow. So this is going to be alpha emitted. So it's emitting alphas. The second one, where is beta compared to the arrow? It is to the right of the arrow, therefore it is being emitted. In our last example, where is beta compared to the arrow? It is to the left of the arrow. This means that silver is taking it in to form PD. So therefore the beta is being captured. Take a second, review this, make sure you understand the whole left and right and alpha beta thing. Now, fission and fusion. They are the exact opposite of each other. Fission means the atoms tend to split. Key word that you need to highlight, split into smaller atoms in order to increase their stability. So you have one huge atom that cannot handle being so big that it splits up into smaller pieces. Now, when this happens, a nuclei of certain isotopes will undergo fission when bombarded with neutrons. So uranium, for example. Uranium is perfectly fine when it's sitting there by itself. But if you bombard it with a neutron, meaning you're adding a neutron to it, it causes it to become unstable, which then therefore causes it to split. Now, in this picture, you see that it splits into two isotopes, but then it also releases more neutrons. Where do those neutrons then go? It causes a chain reaction. So this is shown in the next picture. Those three neutrons hit more uraniums, which therefore break more and hit more uraniums and keep on going. This is how the atomic bomb works. So more neutrons are released and cause a chain reaction. You pack enough uranium isotopes into a compact pressure container, you bombard it with neutrons, and bam, you blow up a city. Fusion, exact opposite. You fuse something, meaning you're going to combine. So key word, combining of two nuclei to form one larger nucleus. The reaction requires extremely high energies to initiate and sustain a reaction, which means therefore it naturally occurs in stars. Now, radiation in life. You're going to do a project on this and the pros and cons of nuclear energy or nuclear chemistry. So one of the things that you're going to have to take away from this unit is why we use it and why we might not use it. So some of the things that we do use it for, dating fossils, we're able to use the half-life of carbon-14. Nuclear power plants, your bombs, of course. Food irradiation, gamma rays are used to kill off bacteria. Radioisotope tracers, so you're able to put it into your system and based on what it does, you're able to diagnose diseases. And then, of course, radiation treatment for cancer. Now, one of the things you're going to have to do is you're going to have to take a nuclear equation and you're going to have to balance it and solve for an unknown element. We're going to practice this in class. But to just give you a heads up, showing you with this example, you balance a nuclear equation by the sum of the mass number must be equal on both sides and the sum of the atomic number must be equal on both sides. So for this one, if you look at it, 238, arrow means equal 234 plus 4. And it equals. This one, 92, equals 90 plus 2. Now, if I were to make one of these x, you would simply solve for that number, find that number, and then you're able to figure out the unknown.